Hello, advanced algebra students, and welcome back to another video lesson as we continue to explore the elements of exponential growth and exponential decay. And today we're going to be kind of taking a step back in time, but applying a new computation, if you will, to our compounded from our interest and investment chapter. So we're going to be able to solve problems that involve interest that is continuously compounded. So continuously. Before we get there, I want you to try and pause here and see if you remember how to do number 1 and how to do number 2. Okay, number 1, write an explicit formula for the following sequence, where 4 is our first term, and then we go to 4.8, 5.76, 6.912. So the first term, a sub 1, if you will, is 4, but then we got to find this common ratio. What is our common ratio? The R value, we can do 4.8 divided by 4. And then we want to double check, is that the same as going from 5.6 to 4.8? And it should be. I mean, we should get the same for both of them, meaning here is our general explicit formula. The G of any number in that sequence, geometric sequence, 4 times 1.2 to the power of n minus 1. Okay, doing it one less than what we're looking for. More importantly, though, is probably number 2, and going back to some of these interest problems. You put $4,000 into your account with a 2.5% interest rate compounded monthly. Compounded monthly, that's a 12. Assuming no additional deposits or withdrawals, you're not putting any more in or taking any more out, how much will be in the account after 8 years? All right, if you remember, we start with this part of our formula, right? A equals 4,000, our starting value, times 1 plus the rate as a decimal, divided by the number of times it's compounded, to the power of 12 times how many years? The compounding times the years, which should have given you a final value of $4,884.59. We're really going to be investigating a lot of what this type of problem, number 2, means for compounding continuously versus monthly. And that leads us to where we're working out of in the packet, page number 5. To help us understand what's happening with a compounding problem, that is continuous, let's look at investing $1 into a bank account and just looking what happens over time. All right, annually, meaning we get the compound interest just once. So that would be the formula. That means we have $2 the next year. If I did it semi-annually or twice within the year, I'd actually have $2.25. All right, if we did it quarterly, we'd have a 4, right? And so we could fill in 1 times 1 plus 1/4 to the power of 1 times 4, which is 4, or you get $2.44. Monthly, we'd be doing it 12 times. Daily would be 365 times. Hourly, how many hours are there in a year? Oh boy. Well, there's 24 hours in a day times 365 days would be 8,760 hours. So that would be the compounding. You'd be getting it every single hour for the entire year. If we wanted to figure out by the minute, we would have 525,600. That's how many minutes are in a year. Right, and then we'd have to use these numbers up in here. So why don't you take a minute to pause the video here and see what do you get for these values in the right-hand column if that's what we're compounding. All right, by my account, we're going to get 2.6130 with a bunch of other numbers, 2.613. Then we're going to get $2.71.456. Then all of a sudden we get 2.71812. And then we get the same thing almost here, 2.71827. A little bit more, but it's here's what's happening, right? as we keep compounding it smaller and smaller and smaller, because this number gets larger, we're compounding it more and more and more often, really this amount of money would still be $2.72, $2.72, and it would probably carry on that way for a very long time. Okay, because what we end up doing is compounding it continuously, as we call it. It's just continuously growing. And so eventually we need to use a different representation for that. And that's where this letter E comes into play. E in math is actually a number. Okay, it's this number, 2.71828. It's just like pi in that it goes on forever and ever and ever. And we can use this E value in some of our equations when the compounding is continuous. Okay, when it's continuous. Typically when it's more than like a month or something like that. You do have that on the Inspire, e to the power of x, so you can hit e and then to whatever power. Or we can use this on Desmos. And so we'll kind of, figure out how to use that on Desmos in a second, okay? But if we want to find the approximate value of E, we would type e to the power of 1, which would give us that value, all right? E is really a number. It's just like pi. So we can evaluate things that have E in it by rounding, all right? So E squared to the nearest hundredth. I'm going to go over to Desmos, and let's do E to the second power. 7.389. 7.389. Oops, let's grab this. 7.389. If I'm rounding it to the nearest hundredth, we get 7.39. Okay, so we can type these into Desmos, or you can use that E function on your calculator. E to the negative 3. All right, so instead of to the 2, I'm going to raise it to the negative third power. Notice we don't get a negative number, really. We just get a really tiny decimal, 0.05. 0.05. All right, why don't you try the last one? 2.7 times e to the 1.4. 2.7. So we type in 2.7. Whoops. 2.7 times e to the power, what did I say, 1.4, I think? Yep, of 1.4. 10.95. 10.95. So we can evaluate things that have E in it because really E is just a number. It's a numerical value for that continuous compounding. And even in these problems, we have to do e to the power first and then multiply by 2.7 in the correct order of operations. Now, here's a new formula that we're going to use for some of this interest, but only when it's continuously compounded. The formula will be A, our amount equals P times e to the power of RT. E to the power of RT. Okay, and we say that it's continuous when we get something maybe more than monthly. All right, and we should know all of these variables already. P is the principal, our starting amount. R is the interest as a decimal. And T is time in years. How many years are we getting this compounded continuously for? Where e to the R is the growth factor. That's how much we're growing by. Okay, and so we can evaluate certain things continuously if we use E. For example, if we compare to our warm-up said $4,000 in an account, 2.5% interest rate compounded monthly. So we used 12 for 8 years. What happens, though, if we change it and say, well, what would happen if we compounded continuously? And again, the formula is our amount equals P times e to the power of RT. The principal is 4,000 times e to the power of what's our rate? 0.025 times how long? Times 8 years. And if we type that in carefully, we can type that into Desmos and come up with a final value. So let's clear this. Our starting amount was 4,000 times the e to, oops, not squared, e to the power of 0.025 times 8 years. Okay, notice how all of that is still up here to the power of e. And we get $4,885.61. 48.85.61. $4,885.61. So we do have more, and it's not substantially more, $1.02? So it is a little bit more by compounding it continuously, but it's not like it's going to be a super big amount. All right, but we do have to make sure we use the rate as a decimal, and time is the time that it's going to be in the account if it's compounded continuously. Last example is, well, what information do we have, and how can we maybe write a situation or analyze what's happening? So in letter number 1, what does the 9,000 represent? That's our starting value or principal. So we have this starting principal of $9,000. We have a rate that equals 4%. Right? It says 0.04 in the equation, which means it's 4%, and it's going to be in the account, in this case, for T years. So we could make up some story problem, right? Mr. Goodacre has $9,000 in an account where he's going to be earning 4% interest compounded continuously for T years, right? And we could do the same thing here on number 2, $500 for a principal where the rate is 2% over T amount of years for T years, so that we can plug in a value to see how much that would be worth after T years. So a little bit of review is just this new letter E that does represent a numerical value in helping us find this compounded continuous interest. If you have any questions, please make sure that you reach out. Otherwise, until next time, everyone, stay safe.